Good morning, students. Today we will discuss problems based on invariant points and some of the properties of bilinear transformations. So our first problem is, what is the form of bilinear transformation which has one fixed point alpha and other fixed point infinity? Now, we are having two fixed points. One fixed point is finite and another is infinite. And we already discussed in such a case, for the transformation, W is equal to AZ plus B upon CZ plus D. We have this C0 and A minus D non-zero. So putting C is equal to 0 here, this transformation takes the form W is equal to AZ plus B upon D. It means W is equal to AZ upon D plus B upon D. Now, alpha is one of the fixed points of this transformation. So by definition of fixed points, W will be replaced by alpha here and Z will also be alpha. So that will become alpha is equal to A upon D alpha plus B upon D. Now let us subtract the two equations 2 and 3. So we get W minus alpha is equal to A upon D into Z minus alpha. Now A and D are constants. So let us take A upon D is lambda. So this equation becomes W minus alpha is equal to lambda into Z minus alpha. So this is the required form of the bilinear transformation, which has one fixed point alpha and another fixed point infinity. Now our next problem is to find the fixed points and the normal form for the bilinear transformations. So the first one is find the fixed point and the normal form for the transformation W is equal to Z upon Z minus 2. So let us find fixed points. So by definition of fixed points, let us replace W by Z here. So this equation will become Z is equal to Z upon Z minus 2. Cross multiplying and simplifying, we get the equation Z square minus 3Z is equal to 0. So we get two values of Z, which are 0 and 3. These two values, they are the fixed points of the bilinear transformation. Now we have to find the normal form. As we discussed in the previous theorem that when we have two distinct invariant points, then the normal form is given by W minus P upon W minus Q is equal to K into Z minus P upon Z minus Q. Here P and Q, these are the distinct fixed points for the bilinear transformation. Here the values of P and Q are 0 and 3. So let us find the value of this expression. So let us consider W minus 0 upon W minus 3. Now W minus 3 is given by the value of W is Z upon Z minus 2. So W minus 3 will become Z upon Z minus 2 minus 3. Taking LCM and simplifying, we get the value of W minus 3, which is given by minus 2Z plus 6 upon Z minus 2. Let us substitute this value in this expression, W upon W minus 3. Putting the value of W and W minus 3, we get the form minus 1 by 2 into Z upon Z minus 3. Now let us compare this expression by this form. So we get the normal form of the bilinear transformation, which is given by w minus 0 upon w minus 3 is equal to k into z minus 0 upon z minus 3. This k is minus 1 by 2. Now, in the next part, we are to find the fixed points of the transformation w is equal to 3 iota z plus 1 upon z plus iota. So let us replace w by z, and after cross multiplication and simplifying, we get the equation z minus iota whole square is equal to 0. So we get two values of z which are same. These are iota and iota. It means there is only one distinct fixed point, which is iota. Now, to find its normal form. So when we have only one invariant point, in that case, normal form is given by 1 upon w minus p is equal to 1 upon z minus p plus k. P is the invariant point. Now here, in our present case, the value of p, that is iota. So let us find 1 upon w minus iota. And we are to represent it in this form 1 upon z minus iota plus k. So let us find w minus iota. Now w is 3 iota z plus 1 upon z plus iota. So w minus iota after simplification becomes 2 iota z plus 2 upon z plus iota. Taking reciprocal, we get 1 upon w minus iota is equal to z plus iota upon 2 iota into z minus iota. Now, dividing z plus iota by z minus iota, that can be written in the form 1 plus 2 iota upon z minus iota. Multiplying, we get 1 upon w minus iota is equal to 1 upon z minus iota by 2. So this is the required normal form in this case. Now, our next theorem is, if alpha and beta are two given points and k is a constant, then show that the equation z minus alpha upon z minus beta mod is equal to k that represents a circle, provided this k is not equal to 1. To prove this, let us square both sides in this equation. So we get z minus alpha mod square upon z minus beta mod square is equal to k square. Now we know that z mod square means z into z bar. So z minus alpha mod square means z minus alpha into its conjugate. Z minus beta mod square means z minus beta multiplied with its conjugate. Now, cross multiplying and simplifying this expression, we get the form z into z bar minus alpha minus beta k square upon 1 minus k square into z bar minus conjugate of alpha minus beta k square upon 1 minus k square into z plus alpha mod square minus k square into beta mod square upon 1 minus k square is equal to 0. Now, this equation is of the type z into z bar plus b into z bar plus b bar into z plus c is equal to 0, which represents the equation of a circle if k is not equal to 1. Now, in the next theorem, we proved an important property of bilinear transformations, that a bilinear transformation maps circles or straight lines into circles or straight lines. So let us take the equation of a circle with P and Q as its inverse points in complex plane Z. equation of circle is given by z minus p upon z minus q mod is equal to k. Here k is not equal to 1. If k will be 1, this will represent a straight line. Now let us take the bilinear transformation is given by w is equal to az plus b upon cz plus d. Now from here, after cross multiplication and simplification, we can find the value of z, which is given by dw minus b upon minus cw plus a. Now this bilinear transformation transforms this equation into the form after putting the value of z here. So putting the value of z here, this will become dw minus b upon minus cw plus a minus p upon dw minus b upon minus cw plus a minus q mod is equal to k. Now let us take LCM, and from the numerator let us take d plus cp common, and from the denominator let us take d plus cq common. So this expression will take this form. Now in this form we can take the expression ap plus b upon pc plus d denoted by p dash, and the term aq plus b upon cq plus d, that is denoted by q dash, and this whole term that is denoted by k dash. So finally this takes the form w minus p dash upon w minus q dash mod is equal to k dash. Now even if k is 1, even in that case this k dash is not equal to 1. So we can say that this equation 3 that represents a circle in the w plane, and in particular when k is 1, in that case this equation 1 that represents a straight line. So for k is equal to 1, the bilinear transformation transforms this line 1 of the z plane into a circle of w plane. So this is one of the important properties of bilinear transformations.